Okay, everybody. Good morning to you. We're going to move on today to nucleic acids, but before we do that, I wanted to finish up with just a little bit about cholesterol biosynthesis because this is an important pathway and it made Pfizer $125 billion, and so it's useful to think about. Um, so, about Pfizer and statin drugs. We'll get to the cholesterol synthesis, but a lot of the drugs that are prescribed to lower cholesterol are inhibit a step prior to the synthesis of these two terpene subunits, dimethyl allyl pyrophosphate and isopentenyl pyrophosphate. So the statin drugs inhibit a step along the way to these intermediates. I'm going to show it to you not because, maybe I won't show it to you actually, but not because it's particularly, scratch that. I'll have to do that later. Anyway, so we've talked about how you can condense terpene units together. And in general, doing this involves what we're going to call sort of head-to-tail condensation. That is, both of these terpene subunits have sort of directionality. You've got a tail that sort of is a dimethyl tail, and then you've got a polar head group. And when we add these two together to get geranyl pyrophosphate, we're linking the tail of one unit to the head of another. All right, and this is geranyl pyrophosphate. And we've talked about how you can then take that and add another unit of isopentenyl pyrophosphate. And you can get the molecule with 3 isoprene units. And this is called, as we talked about last time, farnesyl pyrophosphate. And so far, you can see that the head of one pyrophosphate group is linked to the tail of another, and we can highlight these individual isoprene subunits. So at this stage, we've got 15 carbons, and in order to make cholesterol, we're going to need 30. And so you have an enzyme that will make this happen, and I'll show you the resulting product. Kind of painful to draw because it has so many carbons. Oops. 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So far this looks like just any old terpene. And let's see, I need another color, maybe red. But at this stage, the bond we make between sort of the head part of one terpene unit is going to actually be bonded to the head of another terpene unit. So now we're going to go 5, 4, 3, 2, let's see, yep, 5, 4, 3, 2, 1. Whoops. So now we're going backwards. And I can't hardly even do this. All right. So one of the interesting features of this reaction is that you're going to join 2 molecules of farnesyl pyrophosphate together, but instead of having them be added together head to tail, their head groups are linked to each other. And if you look at what farnesyl pyrophosphate is, both of the head carbons are at the sort of alcohol oxidation state. And so, whereas in the product, they're now, there's no alcohol. They're sort of in a reduced state. So the reaction that condenses these two together is a reduction reaction. You don't need to worry about the mechanism or the enzyme that does this. It's called squalene synthase, but it uses one molecule of NADPH, and usually when people, at least in biochemistry, say that NADPH is being used, there's usually a proton transfer that has to happen as well. So they'll write it like this, even though we know better, there's no such thing as a hydrogen ion floating around by itself, but that's just meant to balance the equation. In any case, it's a reduction reaction that allows you to take two basically alcohols and link them together head to head. And that mechanism is known, and it's kind of interesting. So if you want to know more about it, I'll need to look it up before we talk, but I have been through it before, I just forgot it. But it is interesting, but we're not going to talk about it in this class. What you've got now is, and I forgot double bonds, so my apologies there. What we've got now is a 30-carbon precursor, and I'm trying to highlight here all of the different isoprene units. So we're running out of colors. Let's maybe go, no, whatever. Okay, so there's our 30 carbons, and this is called squalene. Not sure why. But it's got 6 isoprene units, so we would call squalene a triterpene. Now, what's going to happen next is somewhat bewildering, but I want you to pay attention to just how set up this molecule is for the reactions that are going to happen. Because we're going to see a lot of 6-membered rings formed, but you're going to see that the way squalene is built, it has to happen that way. Things are positioned such that the right bonds will form, and it has a lot to do with carbocation stability. So before anything else happens, there's an oxidation step. It involves molecular oxygen and FAD. We won't talk about the mechanism. It's basically epoxide formation, and the enzyme that does this that you don't need to know is squalene monooxygenase. But what that does is it takes squalene and it puts an epoxide at this carbon. And it happens to have this stereochemistry, which is controlled by the enzyme. Yeah. Okay, so this is squalene epoxide. And we know that epoxides are electrophiles, right? And you learned in 351 that epoxides, when the 2 carbons in an epoxide are different, the regioselectivity of a nucleophile attacking sort of depends. Okay, do you remember where do strong nucleophiles attack epoxides? At the less substituted carbon because sterics, right? But there's another mechanism, another possibility. You can first protonate the epoxide, and then if you protonate it first, then what gets attacked? The more substituted carbon, because once you protonate the OH group, the bond with the more substituted carbon lengthens. The oxygen sort of leans over, doesn't leave entirely, but it puts a substantial partial positive charge on the more substituted carbon where it's more stable. All right, so knowing what you know about 351, already you should be predicting that that epoxide is reactive at the more substituted carbon. All right, now this is going to be what we're going to do now. I'm going to have in the notes, so if you struggle to draw it, that's okay. I brought it, well, I had already had it written out, but I think probably it's better just to draw it out together. Whoops, how do I get rid of this? There we go. All right, so we're going to redraw squalene, and we're going to draw it in a way that shows the bonds that are close to each other and sort of gives us an idea of the structure that's going to happen. So I'm starting with the pink subunit. Whoops, I didn't like that, sorry. Starting with the pink subunit again. So this will be 1, 2, 3, 4, 5. And we'll go ahead and show the epoxide here. That's sort of in front. The epoxide is down here, but it's up here because we've peeled that part of the molecule and twisted it around in front of us. Okay, this will be, I'll use red for the bond between two isoprene units. And then we'll use the orange unit. This will be 1, 2, 3, 4, 5. So that's crudely drawn, but you can see the beginnings of a 6-membered ring there, right? And you can see how if we protonate this epoxide, the carbon that's going to be electrophilic and have the partial positive charge on it is very close to the alkene, right? And so you can imagine that alkene acting as a nucleophile and attacking the more substituted carbon to make a new bond between orange 4 and pink 2. But notice that doing so is going to leave a positive charge on the more substituted carbon. So this thing is already set up to make a 6-membered ring, and all of the regioselectivity issues are taken care of for you because of the structure of the terpene, because of the positions of the methyl groups. The carbon that's going to be reactive as the electrophile is reactive because of the 2 methyl groups. The alkene that's going to be a nucleophile, we're going to control alkene addition regioselectivity by virtue of the fact that it's better to make a bond between 4 and 2 here so that orange 2 gets the positive charge. All right, but before we do that, I'm just going to show you the remaining portions of the molecule. We're going to draw what comes next in a slightly different way. This is going to be the sort of red subunit. That's ugly. Should I try again? All right, so that's 1, 2, 3, 4, and 5. So that's the first 3 subunits of first 3 isoprene units of squalene. And then here is the next bond, but this bond is not going to be between 5 and 1. This bond is between 5 of one isoprene unit and 5 of the other. This is the head-to-head bond that I was telling you about. So we'll start here, and this is now the green isoprene unit. 5, 4, 3, 2, 1. Okay, then another bond between the 2. Then comes the blue isoprene unit. 5, 4, 3, 2, 1. And then lastly, 5, 4, 3, 2, 1. So let me label the rest of those. Okay. Okay, questions so far? It's kind of complicated to draw it that way, but I wanted to arrange it in a way that helps you see what happens next. Your text is going to show you all of this in a view from above, and it might be kind of confusing, so I thought we'd take the sort of sideways view so that you can see all of the six-membered rings forming. Any questions so far about structure? Okay. Daylight savings time is so terrible, isn't it? My grandpa, yesterday we were eating at my mom's house. My grandma said that my grandpa had changed all the clocks, but he changed them all the wrong way, like backwards instead of forwards. Fortunately, they caught it, but when you have kids, it plays even greater havoc because the children don't know what time it is. They just know when they're tired and hungry. So get ready for a lifetime of daylight savings time misery, unless you call your representatives and tell them to get rid of it. But understand you're fighting against, I'm sorry, this has nothing to do with chemistry, but you're fighting against the vacation and hospitality industries because they like the spring forward thing, because then it's light more after work, and then people, and the change makes people think, oh, it's getting to be spring and summer, let's go outside, let's go to ball games, let's spend more money, let's go on vacation. So economic interests. I also remember hearing, and this was years ago, daylight savings, or going back to the regular time, the fall back used to happen about the time of General Conference in October. But then the candy industry lobbied Congress to push it back even further because they wanted it to be lighter later for trick-or-treating. And supposedly all of the senators got a big plastic pumpkin full of chocolate and stuff. So our tax dollars at work, sorry. Okay, so I'm just going to go ahead and finish labeling the rest of the carbons here. And afterwards, 5, 4, 3, whoa, what the heck am I doing? Five, 4, 3, 2, 1. 5, 4, 3, 2, 1. And 5, 4, 3, 2, 1. Okay. So we're going to do this step by step, though your text will show it all at once. The reactions I'm going to show you here, you're used to thinking of reactions as having a single transition state and then an intermediate and then perhaps another transition state and another intermediate. And we're going to show it as though it's that way, though in reality, the reactions I'm going to show you have a pretty long and flat transition state with almost no intermediates. So you can describe what I'm going to show you as happening in one concerted step. It's hard to imagine that that means they're simultaneous. And so to keep track of what's going on, we're going to draw intermediates. But understand your text is going to show what I'm going to show you next all at once. And the reason it does that is because there's evidence that all of these things happen at similar energy levels. There's not really any intermediates along the way. Okay, so we're positioned now for the alkene between orange 2 and 4 to attack pink 2 at the more, that's attacking the epoxide at the more substituted carbon. All right, let's draw what would happen after that. I understand that you're not going to be able to keep up in your notes with this because I'm copying and pasting, and I'm sorry about that. All of this is going to be posted online, and then you can also view it in the text if you like. So the new bond we just made, we'll use this blue color. And it might be helpful as we do that to redraw the carbons here. So we just made a new bond here. And that's our first 6-membered ring. And that leaves a positive charge on more substituted carbon 2 where it's more stable. Okay, so that's sort of our first ring. But as soon as that happens, look what else we've got. We've got a positive charge on carbon 2, and that is 1, 2, 3, 4, 5, 6 atoms away from carbon 4 of another isoprene unit. And lo and behold, that alkene that could be the nucleophile is positioned so that we'll make a bond between red 4 and orange 2 so that the positive charge can be on red 2, which is more stable. Okay, well, let's give that a try. I'm going to use a blue arrow now just to indicate the bonds that we're making. So again, we have an intramolecular attack of an alkene on a positive charge. I'm going to copy this now. And once I've shown you all the individual steps, I think I can probably go back and show you how most people draw it. So we've made a new bond. Whoops. Between these two carbons. That's kind of ugly looking, but we'll redraw that later on, and it's a 6-membered ring. Okay, and we now have a positive charge on red carbon 2, and we now have the alkene of the next isoprene unit positioned so as to be near that positive charge. Now there's a difference. See, now that we've linked together the red and the green isoprene units head to head, now the carbon of the alkene that is closest to the positive charge is the more substituted one. You could imagine carbon 4 attacking red 2, but if that happens, you would make a less stable 6-membered ring instead of a less stable 5-membered ring instead of a 6-membered ring. Notice there's 1, 2, 3, 4, 5 atoms here. So what we're going to do is basically an anti-Markovnikov addition, and why this happens has to be because of the offset instability between a 5 versus 6-membered ring and between a secondary versus tertiary carbocation. And then our cop-out answer will be the enzyme directs it to be this way because, for whatever reason, nature prefers to have a 6-membered ring at that position. All right, so let's draw the new bond we just made. And that will be between carbon 2, green 2, and between green 2 and red 2. And that will put a positive charge on 4. And then, again, we've got a double bond positioned just the right amount of distance away. And if we have carbon 4 do the attacking, we can get a 5-membered ring with a positive charge on carbon 2. Now, why? Again, nature could have chosen something else at this stage. Nature could have chosen to have 2 attack to give a 6-membered ring. I don't know why, other than the enzyme makes it go this way. So the new bond we make is here, 5-membered ring, with a positive charge on carbon 2. Okay, so in that process, from where we started with the epoxide to where we are now, we've stitched together 4 rings. We've made 4 carbon-carbon bonds, and we've made 4 rings. And for fun, I will show you what your text will show you in terms of how this sort of happens. Your text is going to use a cascade of arrows where there are actually no carbocation intermediates, and is going to go directly to this cation here. I will also show you the structure of the molecule we've just made while looking at it from above, so that you can have a sense for the complexity of what we've just introduced here. Oops. That's like totally wrong, sorry. Okay. And I won't highlight the individual isoprene units over here, but you can go back and do that if you'd like to. So now we've made this elaborate system and we have a positive charge there. Okay? But that's not all. There's more pain. Okay? We've established the core structure of steroids and cholesterol, but we've got methyl groups and everything in the wrong place. So now your favorite thing, a carbocation rearrangement, is going to happen. And like what we just barely did, it's going to be a cascade of reactions. So you learned in 351, well, actually, before we do that, any questions about the bond forming processes here? Yeah.
Why was there a 5-member ring formed instead of like the favorable 6?
Yeah, so on the last 2 rings that we formed, in one case, we preferentially formed a 6-membered ring, even though that would put a positive charge on the less substituted carbon. And then, in the next step, we formed a 5-membered ring, presumably to avoid putting positive charge on the less substituted carbon. So why does that happen? It could be because the active site of the enzyme can't accommodate the size of a 6-membered ring at that point, but that's sort of hand-wavy, and I'm sort of making that up. So the answer is I don't know. Probably because you don't actually have carbocation intermediates, but this happens all in the same step. Probably it's not so bad to have a secondary carbocation here. In terms of why we form a 5-membered ring versus a 6-membered ring, I got nothing there. Yep. Yes?
Why doesn't that last isoprene unit form another 5-membered ring?
Yeah, why doesn't that last isoprene unit form a 5-membered ring? Because you could, 1, 2, 3, 4, 5. Did we get the number of bonds right? Come on. Yeah, 5, 4, 3, 2, 1. You could imagine attack from here. If it happened directly between here and here, I think that would be a 1, 2, 3, 4-membered ring. You could maybe make a 5-membered ring. I don't know why nature doesn't do that. It's a good question. In part, we're going to see that cholesterol behaves kind of like a lipid. It's got sort of a polar head group and then sort of this nonpolar structure, and it can be incorporated into membranes. And actually, cholesterol can change a lot about membranes, so it's important. So maybe having that tail is some kind of use. I'm just speculating, though. What else? Okay. You ready for carbocation rearrangement? So what happens next, I'm going to show from this perspective. In 351, you learned that when you have a positive charge on a secondary carbon that's adjacent to a tertiary one, you can do a 1,2 hydride shift to get the more stable tertiary carbocation. Similarly, you were taught that when you have a secondary carbon adjacent to a quaternary carbon, you can have a 1,2 1,2 methyl shift to turn to get a more stable tertiary carbon, right? This kind of stuff sound vaguely familiar. What you didn't focus on a lot in 351 was whether rearrangements can happen when doing so would give you carbocations of similar stability. And we sort of oversimplified to you and told you not to worry about it, but it is biologically important. So you've got the positive charge here, and on the adjacent carbon, you've got a carbon-hydrogen bond. And if I move this over via a 1,2 hydride shift, that would place a positive charge on the adjacent carbon, but we're just exchanging one positive charge, one positively charged tertiary carbon for another tertiary carbocation. So that 1,2 hydride shift is going to put a hydrogen here and going to put a positive charge there. And then this hydrogen is going to lean over and do a 1,2 hydride shift. And that would create a positive charge here. And then this methyl group is going to lean over and do a 1,2 methyl shift, which would put a positive charge here. And then this methyl group is going to lean over and do a 1,2 methyl shift that will finally put a positive charge at this carbon. And presumably the purpose of all of this is to get a positive charge in the right place so that we can do an elimination reaction. So now we have to draw everything where it ended up. Interestingly, stereochemistry is preserved during these 1,2 hydride and methyl shifts. So this proton is down, and after the shift, it is going to continue to be down. This methyl group is up, and as it leans over, it's going to continue to be up. This methyl group is down, and as it leans over, it's going to continue to be down. And then that puts a positive charge here. And some of the reasons for this 1,2 hydride shift, we haven't talked about it, but this may be about also getting the 5- and 6-membered rings to adopt the right conformations by changing the stereochemistry of how they're linked together. Finally, when you get to this carbocation, a base removes the adjacent proton to give you a double bond at that position. Now you could ask, why don't the 1,2 hydride shifts continue? How would I know to stop? Well, you don't. And so we're not asking you to predict that this happens, just be able to explain how it happens given that it does. Sorry, I copied the wrong thing. So our final molecule has the double bond there, and this is called linosterol. And that is not even cholesterol, because there are 19 more steps before you get to cholesterol. And then from cholesterol, you can make other things like hormones, and you can make bile salts. And hormones include estradiol and progesterone and testosterone and also cortisone and some other variants. And so a lot of things come from this pathway. But I think it's an interesting example of how a simple, relatively simple linear precursor and very simple starting material subunits get stitched together, and then the pattern of methyl groups and double bonds in this structure sets you up perfectly to make the fused rings. Okay. Do you need to memorize the structure of all of these intermediates? Clearly not. Because you're not going to be drawing really anything on a multiple choice exam except on your scratch paper. What do you need to be able to do? Well, you need to be able to discern between reasonable mechanistic steps and steps that are not reasonable. Being able to recognize correct steps that give you the final product is important. Anything else you want to ask about that? Making the bonds, the 1,2 hydride shifts. Okay. Why did we spend so much time on this? I don't know, because I like it. But I think it actually brings together a lot of concepts from both 352 and 351 in a synthetic pathway that makes a pretty complicated molecule. We're going to learn later on when we talk about photochemical reactions about how nature can take cholesterol and convert it into vitamin D. Pretty interesting process, but okay. I think that's enough on lipids. Anything else you want to ask? Please make it stop. I think where you're at. Okay. We'll make that stop. And now we'll go on to nucleic acids. And this is kind of fun because DNA and RNA, DNA is the information storage system in cells. RNA is the messenger, and it's also involved in protein synthesis with tRNAs. And so we're going to learn about how nature transmits that information. Our focus is going to be on structure. Your text does get a little bit into DNA replication, which I'm going to leave for future classes. But we will focus on the structure of the bases and the nucleotides, and we'll focus on the hydrogen bonding pattern. Okay, so first thing you need to know is the structure of the bases. These are the parts, your text calls them heterocyclic bases, and these are the parts that are involved in hydrogen bonding and recognition. So we're going to draw each of them. There are two kinds of bases. There's some that are called purines and some that are called pyrimidines. And you're going to hear people talk about that. And you're going to read it in a biochemistry textbook, so it's useful to sort of know what people mean by that. Pyrimidines are going to be 6-membered rings. And purines are going to be a fused 5- and 6-membered ring together. Okay, so adenine is a purine, and it has this structure. And actually, the carbon and nitrogen bonds in each of these bases is pretty well the same within each class. Okay, so you've got a 5-membered ring, nitrogen here, nitrogen there. Then you've got a 6-membered ring with 2 nitrogens. You're going to have to memorize, I do want you to memorize the structure of the bases, so you're going to have to get used to where these nitrogens are. This nitrogen here is the one that ends up getting bonded to the sugar. We can ask at this stage, is this molecule aromatic? And the answer is yes. The electrons that count include 2, 4, and then this lone pair, 6. Not that one, because that one's held in an sp2 orbital, orthogonal to the pi system. So 2, 4, 6, 8, 10. Not these, because they are also held in an sp2 orbital orthogonal to the pi system. So we've got 10 electrons, and that's right for aromaticity. Interesting features of adenine include, and I'm going to just draw a squiggly line because this is sort of where it's attached to the base. We're going to use red and blue for, red is going to indicate a hydrogen bond donor. That means something that has a nitrogen hydrogen bond that with an electron per hydrogen. And then we're going to use blue for a hydrogen bond acceptor. And in general, this is going to be a nitrogen, a nitrogen or oxygen with a lone pair in an sp2 orbital. So if you look at adenine, we can identify places where there's an H bond donor. That's going to be here. And this group is sometimes called an exocyclic amino group because it's not in the ring, but you're going to hear people talk about the exocyclic amino group of adenine, and that's what they're getting at. And then we have 3 hydrogen bond acceptors. Now, I'll point out that it's these 2 that are involved in Watson-Crick hydrogen bonding. Nevertheless, the presence of these ring nitrogens on these other positions can be important because there are a lot of transcription factors that bind DNA in the major and minor grooves, and they're going to be interacting with these ring nitrogens that are on the edges. Okay, so that's adenine. Notice that adenine only has 2 groups, one a donor and one an acceptor that can participate in hydrogen bonding. The next is called guanine, and it's going to have the same core structure, that is where the nitrogens and the carbons are, only, oops, I missed a nitrogen. Only the pattern of hydrogen bond donors versus acceptors is going to be different, especially on the Watson-Crick sort of face of the molecule. So here's a nitrogen and there's a nitrogen. In guanine, you've got an exocyclic amino group here. So that's new because up in adenine we didn't have that. And then, let's see, you've got a nitrogen-hydrogen bond there, and then you have a carbonyl oxygen there. This system is still aromatic. In the chapter on aromaticity, your text talks about the fact that these electrons can donate and make a double bond here with a negative charge on that oxygen, and if the molecule is aromatic in one resonance structure, it's aromatic in all resonance structures. But notice that guanine has the following hydrogen bond, hydrogen bond acceptors, lone pairs here and here. The lone pair on this sort of amide nitrogen is tied up in resonance with the carbonyl, so we won't worry about it. But this hydrogen, this nitrogen-hydrogen bond is a donor, and then you've got a donor here. Okay, and again, this is the face that's available for Watson-Crick hydrogen bonding. That's the kind of hydrogen bonding that's involved in the DNA duplex. All right, questions so far about those 2 structures? Sorry, I'm trying to label stuff. Fortunately, the biosynthesis of these things is known. Fortunately, we're not going to worry about it. So, there you go. Okay, let's do the pyrimidines real quick, and then you're going to see how the structure of the pyrimidines is complementary to that of the purines. So the first pyrimidine we're going to deal with is called thymine. And there's a version of thymine called uracil that's found in DNA. But I'm going to draw thymine first. So the pyrimidines are a 6-membered ring with nitrogens in this orientation. This one here is the one that's attached to the sugar. For thymine, there's a carbon-oxygen pi bond there. Don't like how I drew that nitrogen. There's an NH bond there. And then there's a carbon-oxygen pi bond there, double bond here, and then methyl group here. So notice that you have donor, donor, and I'm sorry, I'm getting it wrong. You have hydrogen bond acceptor, acceptor, and then in red, donor. I get donor and acceptor mixed up because whenever I say donor, I'm thinking about nucleophile. And whenever I say acceptor, I'm thinking about electrophile, but the language is backwards for hydrogen bonding. The oxygen is nucleophilic, but it's a hydrogen bond acceptor. The hydrogen is electrophilic, but it's a hydrogen bond donor. Anyway, notice that we could pair this oxygen with this exocyclic amino group and this hydrogen with this ring nitrogen in a hydrogen bonding pattern, that they would be mutually complementary. Also notice that there would be one that's not satisfied, but presumably that could interact with other things in either the major or the minor group, I'm not sure which. Uracil is just like thymine, but has no methyl group. Okay, so you can draw uracil. You're just going to copy this and erase the methyl group. And then lastly, you have cytosine. And it also has the same pattern of nitrogens, but its structure is going to be different. It's going to have an exocyclic amino group here, nucleophilic ring nitrogen there, and an oxygen there. Again, here is a hydrogen bond donor, and then here are 2 hydrogen bond acceptors. And notice how what we've got here is complementary to what we've got there. This exocyclic amino group could hydrogen bond with this carbonyl oxygen. This ring nitrogen could hydrogen bond with this NH bond. And then this oxygen, carbonyl oxygen could hydrogen bond with this exocyclic amino group. Notice that you would expect 2 hydrogen bonds in an A-T pair, and you would expect 3 hydrogen bonds in a GC pair. And this is why, if any of you work in labs where you're doing PCR, if you have a oligonucleotide that has a lot of GC pairs, you have to heat it up higher to get them to dissociate, because you're trying to overcome the strength of 3 hydrogen bonds instead of 2. Okay, so I do want you to know the structures of each of these. I do want you to know how they are complementary. For fun, right, who are we kidding? I want you to draw these 2, the AT pair hydrogen bound to each other, and I want you to draw the GC pair hydrogen bound to each other. Okay, so with that, we're done, and I will see you Wednesday.